Hi everyone, my name is Chao Xu. I'm a first-year PhD student from Northeastern University. Today I'm going to talk about my project, Chemcheck, a Cantera debugging tool to detect the chemical and syntax errors in kinetic models. Many important systems have very complicated chemistry, and it is common to make simple chemistry models and feed the parameters to lab reactor data to help us to understand the mechanism behind a complicated system. But it's not always the case, because for some systems like industrial reactors or the rocket engines, it's very complicated and it's hard to be interpreted by a simple kinetic model. So we need to build a more detailed kinetic model. But to build a very detailed kinetic model requires a huge amount of computation that we cannot do them by hand or even the normal computers. Luckily, with the computer science developing, now we can use quantum computation or high performance computing to build the detailed kinetic models with a lot of chemical kinetics modeling softwares to help us to build them automatically. So because of this, the model size has been significantly increasing in the last decade. We can see from the figure that the number of species in the model increased from 1,000 to 10,000 since 2010. So the data of a detailed kinetic model is usually written in CHEMKIN file format, which is developed in 1995 in Fortran language. And back to 1995, every data was written on a punch card. So here's an example of a CHEMKIN mechanism file. So we can see from the file that all the evolved elements and species and the reactions in the model will be included in the mechanism file. And we also need the thermodynamic file to calculate the thermal properties of each species in the model, and the transport file to calculate the transport properties of each species in the model. So as we discussed before, a model can have thousands of species. So with that much of data, how can we interpret and confirm the model? So Cantera can help us to do that. Cantera is an open source software to simulate the kinetic and thermodynamic and transport process. So we can simulate this process by using Cantera and compare the results with the experimental data to see if there's a good consistency so that we can confirm the mechanism of our model. So Cantera can convert the CHEMKIN file format to CTI or YAML format because CHEMKIN is too old and it's easy to introduce a lot of syntax errors. By converting them to the new data format, we can get rid of these errors. Also, we can arrange the data in a better way. And after we have the Cantera input file, we can simulate combustion, ignition, and flames or other physical process in Cantera using our detailed kinetic models by solving a series of ordinary differential equations in Cantera. So here's an example by simulating ignition delay time in combustion in Cantera. So ignition delay time is the time interval between the fuel enters in an engine and the real combustion happening. So during this time, a lot of runaway chemical reactions happen. So it's a very important benchmark for us to validate our combustion model. So Cantera can help us to simulate this ignition delay time, the experimental result. If the two results are similar, that means our model is reliable. So this is just a very basic method about how to use Cantera to validate a model. But a lot of CHEMKIN errors. A lot of CHEMKIN files, they have error, which can fail the simulation in Cantera. And sometimes they're really hard to find. The first difficulty we found is that many published models contain syntax errors that Cantera cannot convert them into the Cantera input file. And also some models have very non-physical parameters because they either merged them from different sources, or they estimate them from quantum computation, or from quantum chemistry calculation, or they made them by automated modeling software. So this can cause the ODE solver in Cantera to crash. And that leads us to our project, Chemcheck. So we developed Chemcheck to help to detect these errors. And it's an open source software hosted on GitHub. And it's mainly written in Python, powered by Django. So users can upload their file on the website and convert them from the website to Cantera input file. If during the conversion, if there's any syntax errors in the CHEMKIN file, it will be reported on the website. And after we have the Cantera input file converted, we can start detecting for the physical errors. So the most common mistakes for syntax errors we found are missing indices or spacing errors. So the first data entry shown here is the normal thermodynamic data entry. And for the second case, we can see that the index number at the end of the first line is missing, and the third data entry, the index number at the end of the first line is out of position. So if this error happen, so if these errors happen, Cantera will stop converting, and Chemcheck will make suggestions about how to fix them. So for the second data entry, if this error happens, Cantera will suggest the user to put the index number at the end of the line, and the third data entry will suggest the user to put the index back to the position. So this is just a simple example about how Chemcheck will suggest users to fix the syntax errors in ChemKin file. And after we have the Cantera input file, we can start checking for physical errors. First is the thermodynamic discontinuity. So this is a data entry, ChemKin data entry for methane. It starts with the species name, and then the species composition, and then the phase of species. And the most important part is these three different temperature points, which divides temperature into two temperature intervals, which in this case, the low temperature interval is from 300 to 1,000. And the high temperature interval is from 1,000 to 5,000. So these first 7 parameters can be plugged in to these 3 equations to calculate the thermal properties of methane in high temperature interval. And the second set of parameters are for the low temperature interval. So if we plot the thermodynamic properties of the species out, we should see 3 continuous lines. But for some models, they have the species with thermodynamic data generates plot with discontinuities at mid temperature. So we can see here's a very serious discontinuity here for the heat capacity plot, and also for the enthalpy plot and the entropy plot. So if you are using Cantera to simulate the process at the mid temperature, it's likely to cause the solver, the internal ODE solver to crash. So Chemcheck can help users to go through all the species in the model and plot all the species with thermal discontinuities out. So this is the result after we use Chemcheck to check for a model made back to 2000. And we can also help to check for invalid PLOG and duplicate reactions. So so what is PLOG reaction? Is the pressure-dependent Arrhenius reactions. So for this type of reaction, each reference pressure point, at each reference pressure point, it has different Arrhenius parameters. So we may need to take the logarithm of this of the of the forward rate constant calculated from each each reference pressure point. So it's very important to make sure that we can generate a positive forward rate constant at each reference pressure points for each reaction at all the temperature points. So Chemcheck will check for the reaction at each reference pressure points to plug these parameters into this Arrhenius expression at these 6 different temperature points to make sure we can to make sure they have all the positive results. So if there's any negative results found, it will be reported on Chemcheck website. So here's the result after we use the Chemcheck to screen for these 2 reactions. We can see that for this for the first reaction, it is invalid. It will generate a negative forward rate constant at these 2 reference pressure points at 500K and 1100 K. And for the second reaction, for the reference pressure point, 1080 M, it will generate negative forward rate constant at 500K. Except this check, so Chemcheck can also help to detect the collision violations. So in order to a reaction to happen, there are 3 prerequisites. The first is the correct orientation, and the second is the enough energy, and the third is the reaction rate must be smaller than the collision rate, because the reaction rate is just the effective collision rate. And for some models, they may have non-realistic rate parameters, which generates a very high reaction rate, which is higher than the collision limit. So Cantera will check for these models and for these reactions and report the rate constant, the forward or reverse rate coefficients, and the calculated collision limits and the violation factors on the web, if there's any violation detects. So if you want to detect for other types of reactions for collision violation, you can Chemcheck will help user to plot the logarithm of rate constants for each reactions, and users can specify the cutoff by dragging this bar to specify the magnitude of the collision limit, and then it's going to filter out all the suspicious reactions, and users can further investigate these suspicious reactions. So here is an animation about how to interact with the plot to find out the possible, the problematic reactions in the model. Except this, we also made some direct change in Cantera to help solve the stiffness of ODE system. So sometimes when the solver crashes, we can see some error message like this, but usually we don't have any idea about how to connect this error message to the real chemical information. So we add the species in the model, which is represented by these component numbers, so that users will know which species is suspicious, and then they can investigate further to see if there's any equations involves this suspicious species, and then check for the rate parameters for each reactions involves this suspicious species. So for future work, we are planning to improve the file editing function and the web UI style on the website to make it more user-friendly and deploy the website, and also add more syntax checks as more errors are found, and improve the interpretation of civil errors message. For example, add problematic reactions directly instead of letting users to deduce them. And the contributions we made, we built an easy-to-use web tool, and we can make suggestions about how to fix the syntax errors in Kinetic model, and we can help to visualize and diagnose the non-physical parameters in the Kinetic model. And we can also help avoid the DoD solver crash in Cantera simulation. So finally, I want to thank to my advisor and all my lab members. And also I want to thank NSF for funding this project. And if you have any questions, I'm happy to discuss about them in the discussion session. Thank you, everyone. Thank you for your time for listening to my presentation. Thanks.